Good morning. Here we are yet again for another lovely session of CENG 4412 Steel and Concrete Design. This is going to be the 11th lecture in the video series, and today we're going to be moving on to a more advanced form of a more advanced limit case for steel beam design or steel beam failure, and that is going to be the study of lateral torsional buckling. So we're going to discuss the theory of lateral torsional buckling, and then we'll be looking at some of the code approaches to it. So first of all, to describe this, I need to look at the concept of residual stress. So I need to consider the topic of residual stress. So what is residual stress? Well, as the name kind of implies, it is a stress that is residual. But what does that mean? So let's talk about residual stress. Effectively, residual stress, it's referring to stresses that remain locked in a section after the manufacture or hot rolling process. So stresses that remain locked in a member. Locked in a member or cross-section from uneven cooling. During the hot rolling process, or uneven cooling following the hot rolling process. Following hot rolling. So consider a generic wide flange shape. Something like this, a crudely drawn wide flange shape. Here. So let us look what happens so consider a wide flange shape. Let's say it starts off red hot, and what happens though as it cools? So let's look at how this shape in general handles cooling. Well, just by their very nature, regions of this shape that have more area around them are going to cool slower than areas that are exposed that have more air around them. So, for example, in particular, here at the web flange intersection, here and here, this is going to cool slowly. This is going to cool slowly. Simply because this particular chunk of metal is surrounded by other chunks of also red hot metal, and so it's going to take a lot longer for this intersection to cool than, say, out here at the flanges. And so then the outer sections, the flange tips, these are going to cool rapidly. Well, rapidly being a relative thing, of course, but this is going to cool rapidly. And just like in any kind of case where you get thermal expansion or contraction, what this is going to do is that this is going to put us into this is going to produce tension and compression. So in other words, if I have fibers here, so in any fibers that cool, well, if you have fibers that cool first, in those you're going to get residual compression. And then in fibers that cool last, you're going to get residual tension. Because the areas that are cooling last, they are trying to, they have already, basically the areas around them have already shrunk prior to them shrinking, so you get a residual tension being locked in them. Residual tension. And so basically you'll end up here. At the flange tips, you'll get a form of compression. So you'll get compression here and tension here at the intersection. And tension. Now, also it is important to keep in mind that this is going to be independent of steel type, or independent of steel grade. This is independent of steel grade. Thermal stresses are not related to the actual material strength, they are a property of the coefficient of thermal expansion. And so what kind of strength of material you have really ultimately doesn't matter in terms of the thermal stresses that are present. Okay, so again, this is a thermal effect, this is a thermal expansion and contraction effect, and this causes stresses to remain to build up and remain locked in a member. Now, it's also important to be in mind that it's important to keep in mind, or important to be aware of, that these stresses are not small. These stresses can actually be quite large. If you see a given steel section, it may look like it's just sitting there not carrying any load, but locked within the fibers of that member can actually be quite large stresses, just sitting there from its manufacturer. So let me give you an idea of some typical compression and tension stresses that sometimes occur. Let's look at some residual stresses here with approximate magnitudes. So here are some residual stresses with approximate magnitudes. So let's look at another kind of generic wide flange shape, although I'll just draw this one as a line diagram. So generic line diagram, wide flange. Like this here. And in the top flange, I would have a mixture of tension and compression. Well, both in the web and the flange, I would have a mixture of tension and compression. So, but basically, at the flange tips here, I would have compression, and at the bottom, I would have at the flange tips, I would have compression, and at the intersection, I would have tension. So you might have something kind of like this. If I were to plot tension versus compression here, so maybe this would be C for compression, C for compression, and this might go all the way up to 20 KSI in some cases. So it might be all the way up at 20 KSI, and then maybe then a reduced value of tension here. Then here in the web, I might have something like this, where this would be maybe 12 KSI compression. You can have stress of approximately 12 KSI, and maybe even in tension here, you can get something like 15 KSI in tension for both basically at the web flange intersection. So that would apply to both this graph and this graph. They'd both be about 15 KSI in tension there. But the point is not that we're ever going to be actually directly calculating these residual stresses. The only way you can't actually directly calculate these. The only way you could detect them, if you wanted to actually know the residual stress, you would have to go and, for example, you would have to go and put a strain gauge on the beam as it clears, etc., etc., and then multiply by modulus elasticity. But you could directly measure it, but that would be quite difficult. But basically, we handle this through other methods than directly measuring the residual stress. The point being, though, not that I need you to remember the actual levels of residual stress in the beam, but just to be aware of what this is and the approximate magnitude of it. So, residual stresses can range at the maximum from between 12 to 15 KSI. So, the real takeaway here is the key thing is that residual stresses are a significant portion of the yield stress. Can be a significant portion of yield, or a significant fraction of yield. A significant fraction of yield. Of yield stress. So what this will mean, though, is that that it can affect our bending moment capacity. So now, also another thing to keep in mind is this is going to be another property of residual stresses. Residual stress is going to be a function of length. Because we know thermal expansion is a length-based effect, so residual stress as a thermal effect, or as a stress that builds up from thermal expansion and contraction, this is going to be related to length. Is a thermal effect. Or not a thermal, I should say a length-based effect, or length-dependent effect. So in other words, if you have a short beam, the residual stresses are going to be very minimal. They're not going to be substantial. But if the longer and longer the beam you have, just like in any kind of stresses involving thermal expansion and contraction, the longer your element, the longer, the skinnier, the more linear your element, the more substantial the thermal stresses are. So that's why this is going to be a failure case, or not a failure case, but it's going to contribute to failure for longer forms of beams. Okay. So connecting to this, I want to describe the residual moment. So if we have residual stress, we can also have residual moment. So residual moment, this would be expressing residual stress as a moment. Residual moment. So I'm going to name something MR. This does not appear in the code, but it is baked into the equations in Chapter F and other places. MR would maybe be the moment of first yield. The moment of first yield. And what would this mean? The moment of first yield including residual stress. Including residual stress. So in other words, if we had a very good map, if we had a very good map for a beam, and we could actually tell exactly for a cross section what the residual stresses are, if I did actually know the precise distribution of stresses in a particular beam, I could go and actually directly calculate the moment of first yielding, including residual stress. Basically, but this is saying that what moment is needed to cause the very first fiber. When you combine the stresses of tension and compression and thermal effects of this cooling effect, residual stresses, what moment is required to actually produce the first yielding in the very first fiber anywhere in the beam? Now, the problem with this, of course, is that this is going to be difficult to directly calculate. So, problem. This is almost impossible to directly calculate. You cannot simply look at a beam. You can't simply go to you can't simply pull a beam off the shelf, look at it, and tell what the residual stresses are to directly determine residual stresses. Now, we do have ways of estimating it. Like I meant, the values that I provided previously. If you wanted, you could actually measure those. But you would need to you would really need to have a set of actually incredibly durable strain gauges literally positioned right on your beam as it was cooling in the factory. So that could be done theoretically, but it's so onerous and so completely impractical that no sane person would ever do that. So instead, we need to do what we always do in cases like this in engineering. What do you think we need to do? We need to make what? We need to make an assumption. Yes, we always do this in civil engineering and other forms of engineering. If we have a very complex problem that is almost always impossible to solve, well, not almost impossible to solve, but a very complex problem that has many variables, often what we'll try to do is we'll make an assumption. Now, we don't want to make too conservative an assumption, otherwise we'll end up building bunkers instead of buildings. But we do make an assumption that simplifies a lot of this, but then makes it, but is still a conservative assumption. So the assumption that we're using for this case, that is built into the steel manual, the assumption here, we will assume that the residual stress is equal to 30% of the yield stress. So we're just going to go ahead and assume that, and where that comes from, if you looked at the previous slide, we said that the residual stresses were between 12 and 15 KSI at the maximum. Well, if you have a steel that is between 36 or 50 KSI, 36 for A36, 50 KSI for something like A992, a 30% residual stress really isn't that bad. So basically, what we're then going to assume is we're going to say that MR, the residual moment, is Fy minus Fr times Rs, our previous elastic modulus, or simply 0.7 Fy times S. Again, if we're assuming that the residual stress is 30% of the yield stress, we're just going to use 0.7 FYS here. Okay. So let's see here. Anyway, and again, so that is sort of our expression for residual moment. Now, this exact expression doesn't appear very often, or maybe you might find it hidden in the commentary somewhere, but where this really appears is this is baked into the equation of lateral torsional buckling that we'll see in a moment. The S again is the S, as a reminder, S is your elastic modulus, elastic section modulus.
You still talk about the x-axis, but you talk about
Sorry, what was that?
you know how the S in the W shape have S for x-axis and y-axis?
Yes.
So in this formula, it would just be the S on the x-axis, right?
Yes. Well, I mean, you can use this formula for either strong or weak axis, depending on which you're dealing with. However, though, if you looked at, you have to consider you have to consider chapter F carefully, because any equation in section F2, it says doubly symmetric. If you look on section F2, it's of course labeled doubly symmetric, compact I-shaped members and channels bent about their major axis. So we're talking entirely about strong axis bending today. So that's the elastic section modulus. If we're and primarily though, so as a reminder, if we are dealing with section F2, then we're going to be dealing with SX, the strong axis elastic section modulus. And again, so here, and again, I just want to have a reminder of this and this will appear later. But as a reminder, I just want to include this. Length matters. This is a thermal effect, so a longer beam directly means more residual stress. Directly means more residual stress. Okay, so let's keep going. Now, next I want to introduce the idea of lateral torsional buckling. So, lateral torsional buckling. What fundamentally is this? So we've mentioned this before, but we actually need to look at this defined. Lateral torsional buckling. So it is a buckling phenomenon. This is not a failure of, this is, when you get lateral torsional buckling, you're not actually getting a failure in any of the fibers. Rather, that what you're getting is a buckling phenomenon. If you remember back to Euler buckling, this is a similar idea, but for compression flanges. Anyway, but let's discuss it. The name really gives it away. Lateral torsional. So let's think about what that means. It is an instability of a flexural member. It's instability of flexural members. Instability of flexural members, and it basically includes a lateral delta or displacement. A lateral delta or displacement of a compression flange and a twisting of the beam cross section. Of the compression flange and a twisting of the cross section. And a twisting of the cross section. So in other words, if you have a cross section here, say you have a cross section, originally it's like this. Well, what is happening when this is under load, when this is under very heavy load? Yes, it could actually fail in plastic bending or something, but instead what is happening is this whole section is sort of rotating and moving down and to the left. So you end up having your cross section more like this. And this is not along the entire length of the beam. Instead, it would be, say, imagine if near the ends of the beam where the beam is supported, the beam is still perfectly vertical. But if you want to visualize this, imagine kind of a twisted beam where at the ends of the beam, it's still nice and vertical and supported like this, but somewhere in the middle, the beam is actually just torqued and bent down like this. It's a lateral torsional buckling. So, in other words, if you were to so if I were to draw out maybe a fixed beam like this, so maybe the cross section here, maybe this would be cross section 1 if I looked at 1 here. Well, actually, let me show this as, maybe this is cross section 2 and this is cross section 1. So 1 would be here and 2 would be here. So in other words, right at the ends where it's braced and supported, the cross-section is still perfectly vertical and perfectly fine. But toward the middle, it's gone and torqued out and sort of collapsed sideways. That's lateral torsional buckling. So you can, this is kind of a it's difficult for me to show you this on a two-dimensional drawing, but this is the basic idea. This is probably the best way I can explain it in a two-dimensional form. Try to visualize this in your head where the beam is at the supports, it's still perfectly attached and fixed and vertical like it should be, but at the middle, the whole thing has bent out and buckled to this downward and to the side. And that's the basic idea of lateral torsional buckling. A few notes on this, though. This is going to be a function of unbraced length, and we'll discuss what that means next. Function of unbraced length. And this can occur either elastically or inelastically, and we will discuss those. Can occur elastically or inelastically. Elastic or inelastic. This can be an elastic or inelastic failure phenomenon. All right. So next, I mentioned this. Okay, so let me annotate this a bit. A function of unbraced length. So this function, what do I mean by this? Well, of course, it means a function, mathematical function. It's going to depend on this, and it's going to depend on unbraced length. So we don't yet know what unbraced length is, although we probably can. You can probably kind of reason it out, hopefully. But we will then look at that in a bit, and this can occur either elastically or inelastically, and so we'll need to see that further. Okay, so next I want to actually define this thing that we refer to as unbraced length. So unbraced length So this is a buckling phenomenon, and if you remember back to mechanics of materials, the best analogy I can give, the more analogous thing here, would be your Euler buckling, your Euler column buckling. And actually, we will revisit that in a week or two when we get to column design, steel column design, later concrete column design. Anyway, this is just like column buckling. This is going to be a buckling of compression flange. This is a buckling of a compression flange. But this is still going to be a function of length. So L is, of course, length. L, when you see L in our equations, L is just going to be the overall length of the beam. However, LB is the length that's important to us, and this is the braced length, or more precisely, the unbraced length. What this means is this is the length between compression flange braces. The length between braces of the compression flange. Of the compression flange. So how are compression flanges braced? Well, bracing can occur a variety of ways, a variety of methods. Often they occur at connections. Connections, specifically fixed connections at beam ends. At beam ends. However, often we also have secondary braces, and we also can also get bracing from beams connecting into girders. From beams intersecting or interfacing with girders. So, for example, consider this. Imagine I have a really nice deep beam made, of course, of good, strong American steel. Good stuff. So let's say I have a beam like this, or sorry, a girder like this, big old girder. And then let's say I have a smaller beam coming into here. Now maybe I'll draw this with kind of a coped web or something like that, or coped flange I should say. Let's just say we have this lined up so that the top of the flanges all line up nicely. So maybe I have something like this, a coped flange like this, and we'll discuss that more when we get to connection design. So maybe I have something like this, a beam coming into this girder, and maybe it's connected with hopefully a better drawn connection. Hopefully a connection that's built better than I've drawn it here, because that looks comically undersized, but anyway. So let's think about this. Now, in reality, this would probably be much taller, and this gap would be and imagine this a little bit higher and closer to there. So anyway, if this thing is going to want to, so this kind of cross section, if this beam here, if this girder here wants to fail in lateral torsional buckling. In other words, if it's going to do that, it needs to be able to move to the side. If this member here, if it tries to buckle to the side, the beam here is going to say, no, you're not going to do that. I'm not going to let you do that. The only way you're going to buckle is if you go through me. And so the only way that this girder can buckle is if it also causes this member to fail, say, in tension or something. So a connection of a beam, a connection will prevent a member from buckling. A girder, say, a girder or beam from buckling at that location, or from failing in LTB at that location. In LTB at that location. Or I should just say, I could say at the connection, at that location. Now, of course, this does raise the question of just how stiff is stiff enough. So, for example, obviously, if I connected, say, a piece of cardboard to a beam, and then imagine if I made this, if this beam here were made out of cardboard, obviously a cardboard cross section would never be sufficient to prevent a big, heavy, strong steel girder from failing in lateral torsional buckling. So, somewhere between, so obviously logically, somewhere between cardboard beam and a beam equal in strength or 10 times stronger than this, there has to be some limit at where it is no longer strong enough, or where it becomes strong enough to successfully act as a brace against lateral torsional buckling. Now, there are equations for that. You can find them in the AISC commentary. For this course, we're again going to simplify and just, normally I'll just tell you if it's going to be adequate in for bracing or not. But if you're doing real design, often you'll need to actually go through the equations and calculate whether it is adequate or not in whether a beam, a given cross-section attaching to something, is adequate to actually prevent lateral torsional buckling at that location. But anyway, but for this case, for our simplifying case for this academic course, we're going to say in most cases, major beams coming into girders, pretty much it's a reasonable assumption that if you have a beam coming into a girder, at least for the sake of this class, that at that location that's going to serve as sufficient bracing for lateral torsional buckling. But if you're taking a more advanced steel, if I were teaching you a more advanced steel design class, say like a graduate level steel design class, in that particular one, I would run you through all the equations of actually calculating whether a particular beam intersecting with a particular girder really is sufficient to be strong enough. Yes?
Can we make this assumption in our ADP? Unbraced length?
In your design project, sure, yes, I'll let you do that. For the students in this class, they're working on a long, semester-long design project. They have a major submission due in a week or so, actually precisely 1 week, covering their beam and girder design. So, yes, I'll let you use that assumption there. That's perfectly fine. Okay, some more examples of discrete braces. So I listed a few, but things that can provide these. Examples of members that can serve as braces. Oh, various things. You can have things like purlins, beams, joists, X-braces, channels, girders, etc. So let me give you a brief example of finding unbraced length. So let us say I had a simple frame layout here. So let's say I have a couple columns here, here, and here. Well, here and here. And here. And let's say, so I should mention here, I guess before I list this, we have two different types of bracing. Generally, we have discrete bracing, which is what I've talked about previously, and then I'll talk about continuous bracing in a moment. Get it? In a moment. Purlins, what are purlins? Who can give me a definition of purlins? They're a member, especially in roofing that you see. They're just a roofing member essentially, especially holding up roof trusses and things like that. Okay. But anyway, just an example here. So this will be an example for calculating discrete brace length. So let's say I have a series of let's say I have girders and beams here. Let's say I have girders. Now, let's say I have beams running this direction. Let's say I have beams running this direction and girders running this direction. Something like this. And then maybe one in the middle here. And in terms of length, let me give some length on this. Let's say this is 20 feet long. Maybe this is a 20-foot span, and maybe this is let's make this completely out of scale, and make this 50 feet long. So I have a big long girder between here and here, and some moderate length beams between here and here. And this beam here and this beam here are going to connect directly to the columns, but this beam here, this is going to intersect and deliver its load to the girder here. And let's just call this girder AB. So the unbraced length for girder AB, now the total length of girder AB, so girder AB, the length is 50 feet. But if this thing is going to fail in lateral torsional buckling, the only way that can happen is if this also causes this to yield. So if this is going to bend out to the side here, the only way that can happen is if it also pulls this beam along. And typically that's not going to happen. So instead, the effective unbraced length is only 1/2. The unbraced length must occur somewhere between. If this thing is going to fail in lateral torsional buckling, that failure will occur along the length between this connection and this column. So the unbraced length here, the unbraced length is going to actually be 25 feet. So the overall length of girder AB is 50 feet, but the unbraced length is going to be 25 feet.
So, just for
Uh-huh.
example, we have two beam in there, so that will be 50 times the 3, like, instead of
50 divided by, oh, if we had, yes, if we had another beam in there, if I had, say, if I had two beams in here, one here, then the unbraced length would be 50 divided by 3.
Okay.
Yes, good question though. Okay, so next I want to talk about continuous bracing, another form of bracing. So continuous bracing. Continuous bracing. So continuous bracing, this is where the lateral torsional buckling really does not apply. So this is the, well, it's kind of in the name, where a beam or girder is braced against LTB really all along its entire length. Against LTB along its entire length. Entire length. So for example, an example here would be something like there's an idea of, a good example of this would be composite design. Composite beam action. There are times when you, again, there are equations in there actually are good equations in the steel manual for calculating this kind of thing. This is a bit beyond the scope of the course, so, but anyway, so we're not going to go in detail calculating this, but it is something I'd like you to be aware of, or that it is something that I'd like you to be aware exists. Often there are times when you can actually design, instead of your steel beam simply passively holding up a concrete slab, there are times you can actually design it so that the concrete slab actually acts as part of your beam. So this is a composite beam. It's a beam made of both concrete and steel. But what you would do is, to do this, you actually have a very interesting way of constructing this. So this is a composite section action using metal studs welded to the top of wide flange shapes. So what you'll do is you'll have your W section, and then you'll have these metal studs that kind of look like this, kind of little mushroom cap type things. And these will be welded to the top of the flange here. And the purpose of this is that if I then on top of this, I will have my concrete slab. On top of this, I'm going to have my concrete slab. I'm going to pour my concrete slab directly on top of my steel beam, and it's going to be directly joined to this thing. So here's my concrete slab. And basically what I then do is I turn my steel section into an enormous reinforced concrete beam. And if I look at this from the side, from the side here, and there are equations that you would use to calculate the required length separation between these studs. Basically, you just have you would have just studs after studs after studs after studs, all in a line. And what this does is, the purpose of these metal studs is that it guarantees that the steel remains firmly in contact, immobilizing the strength, transferring stress between the steel and the concrete. So basically, you end up with just a gigantic reinforced concrete beam. The steel, effectively the W section, takes the tension, and the concrete, the floor slab, that you're actually using see, this is, again, we're not just relying on the floor slab as a, normally we consider the floor slab just carrying the weight and delivering it to beams, but in composite section design, the concrete, the floor slab itself is literally being used as a beam. Now this does result in a very efficient structure. The difficulty is that of course, is that you have to go and send somebody in and manually weld in all of these, across an entire beam. You're going to have some poor guy welding thousands of these things to all over throughout the entire building, and that can be quite involved, very labor intensive. depending on what tools you have available, etc. But so the W section takes the tension, and the concrete floor slab takes the compression. Anyway, that's just an example. This is something neat that you might want to be aware of. But this would be an example of what I would consider continuous bracing, because this thing is going to have a stud every 12 inches, 18 inches, 24 inches, something like that. And so it's effectively continuously braced. It's rigidly joined to it's basically rigidly joined to the floor slab. It's not going anywhere. It's not going to be able to buckle. Other examples of continuous bracing, that's one example, but so again, examples of continuous bracing that you might have. This would be things like concrete deck with studs. That's what we already discussed. Concrete deck with studs. An embedded compression flange. That's where you actually pour your concrete slab literally around your W section. Embedded compression flange. Or I could also use a steel decking with puddle welding. So in this case, you're just frequently welding the steel decking directly to the beam, and the decking, and in turn the concrete floor slab that is poured into the decking will also act as continuous bracing. Now, the important thing about continuous bracing is, while it is usually difficult to achieve, you have to do a lot to get there, but if you do manage to get that, the nice thing about this is that the brace length effectively becomes 0. Your brace length, your unbraced length here, your LB, effectively collapses to 0. If you can manage to continuously brace your section, you are going to have a brace length of 0. Okay. So let's continue. Let us next look at steel beam bending behavior, sort of the grand scheme of things, bird's eye view. So the grand overview of steel beam bending. Actually, I'll say grand overview. The grand overview of steel beam bending. Okay, so let's consider this. Now I'm going to make a generic plot here. On the y-axis, I am going to plot moment capacity, and on the x-axis, I'm going to plot unbraced length. And I can use this as a map that will allow us to sort of walk our way through the section F2 in the AISC steel manual. So this is basically our map through really the rest of the chapter. Well, section F2 anyway. Okay, so on this axis, I'm going to label this unbraced length, LB, unbraced length. Unbraced length. On here, this is just going to be moment capacity. Capacity, or in other words, phi mn. Phi mn. Now, here, I have a few things. I basically have a few things here. So I'm going to make I really have two sort of master states here. Let me draw something like this. Then I'm going to draw something like this. Something kind of like this. And then a diagonal line connecting them. Then a diagonal line connecting them. Okay, so basically I have three regions here. I have 3 regions, and depending on what region we're in, that's the equation that we're going to apply when calculating the moment capacity. One of these regions we've already seen. We saw this last Thursday. And separating these are going to be 2 critical lengths that we'll look at, LP and LR. And we'll learn about these in a bit. LP and LR. And the regions here, this is going to be the plastic region, plastic bending region, just failure in plain old plastic bending. Then we have sort of a transition region, or actually I should say an inelastic lateral torsional buckling. Here we have inelastic lateral torsional buckling, and here we have elastic lateral torsional buckling. And there are equations associated with each of these. Well, also, I want to label 2 sort of points on these, 2 values. This here is going to be your phi MP. And we already learned to calculate this last time. The phi MP, that's the value from last time. That is the purely plastic moment capacity. And you get this mainly when the unbraced length is very small. So if you have a if you actually do have a continuously braced beam or girder, then your unbraced length is 0, and so you will have the full plastic bending moment capacity. And the equation here, so we have that, and then another critical Y value that I want to know. This value here, this is our phi MR, and we saw that previously. And that is going to be 70% of the moment capacity, of the plastic moment capacity. Phi MR, and this is going to be baked into the equations. And so, and basically we have this pure plastic, we have this pure residual stress moment, and then we sort of have a transition region between them. This linear line is really just a transition, a linear transition between them. So we have a transitional region here. This line is basically we have in the region between here, between where the plastic moment and the residual moment state apply, we have a transition region, and this is just a linear interpolation between them. But we'll talk about that more in detail in a bit. But let me label the equations here. The equations here are basically F2-1. Then we have in the middle, we have equation F2-2. And then at the end, we have equation F2-3. F2-3. So basically, what depends. So when we're designing this, when we're calculating our moment capacity, we effectively this drawing basically gives us a roadmap. So the basic idea, the big idea. Maybe I'll do this in a different color. The big idea here is that we're going to do the following steps. 1, we're going to determine unbraced length. Determine LB, and then calculate LP and LR. LP is basically the length that is the length beyond which plastic bending no longer controls. So there's a formula for this, and we'll see that formula and learn that. Some of these are nice, fun formulas, but as we'll see, they can get quite hairy. But these are just some formulas that we work through. This is a formula. So the LP is the length beyond which plastic bending no longer controls. LR is the length beyond which inelastic bending transitions into inelastic lateral torsional buckling transitions into elastic lateral torsional buckling, or it is the length associated with the residual stress moment condition, etc. So but the whole point is that now, and we're actually doing this from a code design approach. this sort of theory really isn't that important. It is important to be aware of how this works, but basically the steps are going to be fairly simple. Well, mathematically maybe not so simple, but mechanically fairly simple. We're going to calculate our LB, and we're going to determine our LB based on our drawings and whatever system we have, whatever floor system we have. And then we're going to go to the code and we're going to run through the formulas of LP and LR, this length and this length. And then depending on where we are in the region, depending on whether we're here, here, and here, we will apply an equation, a moment equation, F2-1, 2-2, 2-3, depending on which region we are in. On which region we're in. We're in. So in other words, so we're going to calculate values for LP and LR. And we would also know our unbraced length. So if we calculate our LP as 20 feet and our LR is 30 feet, if my, so let's say my LP that I calculate is 20 feet and my LR is 30 feet. So again, 20 and 30. If my unbraced length is 10 feet, well then good news, I have the simple equations in the plastic bending region. And again, this is 20 and 30. If my unbraced length is 25 feet, then the equation F2-2 is going to govern. If unbraced length is, say, 35 feet, then I'm in the worst case, the elastic lateral torsional buckling, and I'll be using equation F2-3. Okay, so let's move on. This maybe might remind you of something where, so this, you can see that this kind of falls off rapidly in kind of a exponential decay type thing, or more of a quadratic type decay. And that should kind of remind you of something. This elastic lateral torsional buckling should hopefully, well, maybe remind you of something. If you look on the curve of the elastic lateral torsional buckling, as we saw, it kind of does this kind of behavior like this. But this maybe might remind you of, this is reminiscent, or at least for me anyway, this reminds me of something else. This reminds me of a basic equation from mechanics of materials, the Euler buckling equation. And we will see that in a bit, well not today, but in a week or two. This reminds me of Euler column buckling. And this is where you have, say, a P critical is equal to pi squared EI over L squared. So it's a function, it's an inverse function of the squared length. So similar. And when plotted, it would look very similar to to our lateral torsional buckling. Okay, so let's keep going along. Let's see. Now, next I want to mention the lengths equations. Lengths. So I do want to give you a solid introduction to theory, but I also wanted to discuss some of the code here. Lengths. Lengths. LP and LR. Let's define these. Let me in red instead. So we have LP and LR. And let's name these. LP is going to be our plastic length. And LR is going to be our residual length. And the equations here, the equations to calculate these, well, this is going to be equation F2-5. And this is going to be equation F2-6. And so if you work through the equation, what do we see? So if I go to 2.5 and 2.6, we can find that they are some quite fun equations, especially LR. It's a very fun equation. LP isn't so bad. So in other words, F2-5 here in the AISC steel manual. LP really isn't that bad. It's fairly simple. It's going to be so this is just 1.76 times RY divided by the square root of E over FY. Really not too bad, nice and friendly. But then you scroll down a bit or cast your eyes down a bit to equation F2-6, and suddenly you suddenly don't feel so happy anymore. So F2-6 here, LR, oh, this one's going to be a fun one. This one is 1.95 times RTS times E divided by 0.7 FY. 0.7 FY. Then all of this times, I'm going to put now, this is a very long square root. I could write it out here, but I don't want to squish, so I'm going to write it down here. This square root is basically here, times the square root of JC, that's not J sub C, but just a term called JC, divided by SX times HO. So this is a very long square root. And then inside the square root is another square root. Isn't this fun? And then, then we'll have JC divided by SXHO again. H naught, quantity squared, plus 6.76. This is one of those lovely empirical equations. 6.76 times 0.7 times Fy divided by E. Quantity squared. Now, this does look terrifying, but really this is kind of like, this reminds me a lot of almost like a Pythagorean distance formula, something like that, so really not too bad, and, well, sort of, relatively. Now, this 0.7 E over Fy, that 0.7 Fy, that should be familiar to you by now, or maybe it should remind you of something. That 0.7 Fy, remember, that is related to our residual stress. We said that residual stress was that we were going to assume that it was 30% of the yield stress. So it shouldn't surprise us that many times in our equations here, we repeatedly see a 0.7 Fy cropping up. It's that 0.7 residual stress factor. And there are, and now in order to actually calculate this, there are other things we would need to do, including using, basically there are a variety of factors defined in the manual, including RTS, which we'll need to see somewhere. That can be found in other locations in chapter F here, and a lot of these are thankfully, mercifully, a lot of these are actually included in the manual, or sorry, in the section properties. So for example, if you go back to, if I looked on chapter F here, so for example, our RTS and H naught, these are thankfully already calculated for us. This is effectively RTS. If you read in the manual, that is effectively, this is a radius of gyration related to the compression flange. Radius of gyration related to the compression flange, but it's a section property. So RTS is a section property, H naught is a section property, JC, etc. And you can find all of these discussed therein.
So the JC should be J.
JC, anyway, let's see. Well, it's not J, it's not JC, it's J times C. Sorry about that, J times C. Yeah, J times C. Okay, so J would be the torsional property listed in the manual there. But C would not be CW, C would be your, well, actually, C would be the C. 2.8b, where? Yes, so basically C is going to be your C coefficient, and J is going to be, so C here is laid out in F28A and 28B, 2-8A and F2-8B. That's your C factor. So JC is not, sorry, it's not one thing, but it's we have C, our C factor, our C coefficient, and then J is your torsional property, and that's found on your polar. J is sort of your polar moment of inertia. J, polar moment of inertia. And this also mercifully is also calculated for us in the chapter 1. So basically, this is just a whole series of sectional properties that go into calculating this. I know it looks scary, I know it looks terrifying, but ultimately it isn't ultimately that bad once you get down to it. Okay. So then, depending on what region, so our first step in doing beam design is to calculate these two regions, is to calculate our LP and to calculate our LR. And we will then use those to determine what region we are in. Once we know our LR, our residual length, and our plastic length, and once we know our brace length, we can then know what region we're in, et cetera, et cetera. Okay. So then once we do that, we can then apply the appropriate equation. So if we are in, so again, depending on what region, so again, we use LB, LP, and LR to determine what region we're in. Which region we are in, and what bending failure mode applies. Failure mode applies. What bending failure mode applies? Then we simply apply the correct equation. Well, simply in relative terms. Simply apply the correct equation, or the equation corresponding to that region. The equation corresponding to that region. So, region 1. 1, the plastic region, or sorry, the plastic yielding region, or plastic moment region. The plastic moment region, at the left of our roadmap from earlier, this occurs, fundamentally will occur when your unbraced length is less than your plastic length. And this one is fairly easy. We've already seen this before. This is where equation F2-1 controls. This is where equation F2-1 controls. And where we're just going to say Mn. Now, I'm not going to list all the phi factors on here for all of these equations, and that's because throughout the entire chapter, phi is going to be 0.9. So then, Mn is simply equal to the plastic moment, which is then simply equal to Fy times Zx, the plastic section modulus, times Zx, the plastic section modulus. So that's our first case here. Then, let's see here. Let me talk about the next region on the next slide. So I'll give you a chance to write that down a bit. So again, here in this first region, we are purely in the elastic region. We are in the region, or sorry, not the elastic region, we're in the plastic region, etc. Here. Next to the second region. This is where our brace length is greater than the plastic length, but in turn less than the residual length, less than LR. So LB is greater than LP, but less than LR. And this equation, while it may look a little scary, this is simply going to be just a linear interpolation between the two different moments. So if you remember previously, we mentioned that we had, MP, that's just equal to, say, Fy here, times Sx. And so basically this is going to be an interpolation between MR and MP. Okay, let me just write this out first. Maybe that will make things a little bit clearer, hopefully. So if we have equation F2-3, and this is going to say that the nominal moment capacity, Mn, is equal to Cb times MP minus the quantity MP minus 0.7 times Fy Sx times the ratio LB minus LP divided by LR minus LP. LR minus LP. F2, oh, yeah, sorry about that. That is F2-2, yes. F2-2. F2-2. Now, on the one hand, this looks kind of scary, but note here, look. Remember, this was in the region where if we go back to our, if I sketch out kind of the roadmap again, we had this kind of thing here, flat, curved, and then a linear line between these. Basically, this is the linear, so here we had our, at this level we had our MR, this level we had our MP. This is basically just a linear interpolation between those 2 points. That's all this is. This is just a linear interpolation. This is really just a linear interpolation. Just a linear interpolation. Between let's say LP or MP and MR. That's all this is. It's just a linear interpolation between the two. And I should also mention CB. That's something I may talk about later, but basically that's going to be a moment distribution effect. So that's going to be a moment distribution effect. An effect, that's something I'll talk about in a later video. Okay, I do want to finish this out though. And then I do want to introduce equation F2-3. I do want to talk about the third case, which is going to be where we're beyond. Our length is very, very long, and we're beyond the residual length. So case 3, this is going to be where our unbraced length, LB, is greater than our plastic length, our residual length. LB is greater than LR. And in this case, equation F2-3 controls. So this is going to be equation F2-3. And at first, it doesn't seem so bad. At first. Here, MN is going to be just FCR, F critical, just some critical stress, I wonder what that means, times SX. Nice and friendly, what could go wrong, right? This seems nice and simple. Nothing can be simpler, just a stress value. I mean, very easy, right? What could go wrong? Well, of course, then we actually need to see how they define FCR, and that's where things start getting a little hairy. So for FCR, we need to have an entirely separate equation, and that is equation F2-3. This is equation F2-3. Equation F2-4. And we have this lovely equation, an equation only a mother could love, or perhaps a steel instructor. I like it, but anyway, that's just I'm just weird. FCR is going to be CB. CB, now we will talk about that later, but you can simplify and say, well, you can always be conservative and say CB is 1. But anyway, we'll talk about that in a bit. CB is going to be, so the equation is CB times pi squared E divided by LB divided by RTS quantity squared. And this whole thing times a root, times a square root. Now, thankfully, there's not a square root inside this square root. This is going to be 1 plus 0.078 times J times C divided by SX times H naught times LB divided by RTS quantity squared. And in terms again, some terms here, just as a reminder, I can label these things. E is going to be our modulus of elasticity, our elastic modulus. Now, this is one of those cases where it is exceptionally critical to use correct units. This is a common mistake. I can almost guarantee it that some people make this mistake on the coming exam. I can pretty much guarantee it. It's a very common error. You have to use correct units in this. In other words, you have to use elastic modulus. It's going to have to be in inch KSI. Brace length, it cannot be in feet. It has to be your unbraced length in inches, etc. So basically, all this stuff needs to be in inches and kips. J is going to be your polar moment of inertia, or your torsional constant / polar moment of inertia. But just this is referred to as just the torsional constant / polar moment of inertia. Let me write inertia here. Then Sx, of course, is our elastic section modulus. And H naught is, well, H naught is another section property, but I didn't define it previously, but I can here. What this is this is the distance between flange centroids, between the centroids of the flanges. Between flange centroids. Between flange centroids. Okay. And I want to mention a few other things here. Let's see there. Let's see. RTS here. And let's say this. I could mention CW here. Now, a few other minor notes here on equations. Other minor terms defined. Again, I mentioned some of these previously, but we have that for JC, we have the JC from the previous equation. Well, C again is, we have a few things. We have J is gonna be your constant number 4, your torsional constant. C is going to equal 1 for I shapes. C is equal to 1 for I shapes, and it's equal to H naught divided by 2 times the root of IY, the moment of inertia in the weak axis, divided by CW, CW for channels. For channels here, and CW is also a property defined in the section properties, I believe. CW here. Now here. Yeah, it's another torsion. Is it listed in the torsional properties?
Yeah, J.
Yes. Well, that's C, not CW. CW. Let's see here. Huh? All the way at the end. CW, but is C there? That's not C. That's CW. That's not CW. That's C. So that's, oh no, it's actually included. Oh, it's actually included. Yes, it's in the torsional properties. Yes, sorry. CW. Thankfully, it's going to be included. Now, if you actually want to calculate it, you can. In most cases, you're going to get that directly from the tables. But if you have a doubly symmetric shape, for doubly symmetric shapes, for any doubly symmetric shape, CW can also be calculated by the formula IY H naught squared over 4. Although in most cases you're probably going to rely on the equations in the manual. And also we have another equation where RTS, to calculate RTS here, RTS is going to be equal to, well, RTS squared is equal to the square root of IY times CW, the square root of IY times CW divided by SX. Now, alternately, there's another way you can use this. That's a slightly simpler formula that does make things a little bit easier because it has less sub things that we need to calculate. alternate way of calculating, an alternate but conservative, sometimes more too conservative, conservative equation for RTS. And that is found in the user note on page 16.1-49. You can use the equation that RTS, now the nice thing about this one is that we don't have to calculate any other properties with it. See, this one we need CW and IY, etc. But you can conservatively calculate this as BF, the width of the flange, divided by the square root of 12 times here, basically as the radius of gyration of the compression flange plus 1/6 of the web. But that's expressed as 1 plus 1/6 times HTW divided by BF times TF. But you can find this in your manual as well. I would encourage you to actually do that instead of just writing it down. But anyway. All right, so any other questions on this? Or any questions on this? Okay, I think that'll do it for this portion of the lecture. I will post some follow-up videos today, and those will cover some additional properties, including a worked out example, a longer form actual worked out example for lateral torsional buckling. That'll do it for today, and so I'll see you all later next week, or later this week on Thursday, and as always, thank you.